Welcome. Well, I was just sent this problem, and I figure you can never get enough practice getting the intuition behind intervals of increase, decrease, and inflection points, and minima and maxima. So I'll do another problem, and this was pretty interesting because it has a natural log here, so I thought I would do this one. So let's see, it says f of x with a big F. I like it better when it's lowercase, but f of x is equal to the natural log of x to the fourth plus 27, and find intervals of increase, decrease, find intervals of concativity, and the inflection point. So before I delve into this problem, let's just make sure we understand what we're going to do. So find intervals of increase or decrease. So what are intervals of increase? That means the slope is positive, right? If slope is positive, what does that mean? Increase, so intervals of increase means that the slope is positive, so that means that the derivative is positive. So that means where does f prime of x, where is that greater than 0, right? Increase, intervals of increase is just positive slope. Similar intervals of decrease are just where f prime of x is less than 0. The slope is negative. That's when this function is going to decrease. Not too sophisticated there. Now let's see. Find the intervals of concativity and the inflection points. So what are those? Intervals of concativity. So just a review of what we did before. Where is the graph concave upwards? So I'll write that as concave, con up. Where is the graph concave upward? And what does that look like? Well, that means that the graph kind of looks like that. Well, that happens whenever, what do we know to be true? The slope itself is increasing. Not just the graph is increasing, the slope itself is increasing, right? Because if the slope is negative here, it gets less negative, then it goes to 0, and then it gets more positive, and then even more positive. So concave upwards means that the slope itself is increasing, which means the slope of the slope is positive. And what is the slope of the slope? Well, that's the second derivative. So that means that the second derivative of x is greater than 0. And then similarly, concave downwards is going to look something like that. The graph's going to look like that. And that's periods of the curve where the slope itself is decreasing, right? You have a high slope here, and it gets a little bit flatter, then it goes to 0, then it gets a little bit more negative. So that means that the slope of the slope, or the second derivative, is decreasing. And what are inflection points? Inflection points are points where you go either from concave downward to concave upwards, or concave upwards to concave downwards, and they look like this. So if I was going from concave upward to concave downward, it would look like this. The graph would look like this. I'd be concave up, and then I go concave down. And this point right here is where you switched, and that's an inflection point. Or if you're going, let's say if I were to continue this graph, I'm concave down, and then I would switch back to concave up, this point here would also be an inflection point. And at these points, since we're switching between concave up and concave down, or vice versa, the second derivative is 0. So I'll write that. Inflection points. Inflection points, the second derivative is equal to 0. So let's use this bit of review to solve this problem. So intervals of increase, decrease. So let's just take the first and the second derivative. That's always a useful thing to do. So let's see. F prime, so let me just write f of x. I write in my own handwriting to give me a little comfort, is equal to, and maybe give you comfort as well, the natural log of x to the fourth plus 27. What is the first derivative? F prime of x is equal to, well, let's do the chain rule. Some people go outside in. I do the inner expression, and then I take the derivative of the whole outside. So what's the derivative of this inside? X to the fourth plus 27. Well, that's just 4x to the third, right? The derivative of 27 is nothing. Times the derivative ln of this with respect to this whole thing. So what's the derivative of ln of x? It's 1 over x, right? So the derivative of ln of this whole thing with respect to this whole thing is going to be equal to 1 over x to the fourth plus 27. Or you could say, that's the same thing as, and I'm going to write it this way just because I find this easier in my head to grapple with, 4x to the third times x to the fourth plus 27 to the negative 1 power. I like doing it that because to take the derivative, we're going to take the second derivative now. And to take the second derivative of this, we would have to know the quotient rule. But now we just have to know the product rule. And I know the product rule. I always forget the quotient rule. So let's do that. Let's take the second derivative. So f prime prime of x. And this might get a little hairy. The second derivative. And I will arbitrarily switch colors. So let's do the product rule. So we'll take the derivative of the first expression, the first function. So that's 12x squared. 12x squared times the second function times x to the fourth plus 27 to the negative 1, and then plus just the first expression, right? We took the derivative here, so now we just take it without the derivative here, times the derivative of the second thing. And here we're going to have to use the chain rule to take the derivative of the second thing. So let's take the derivative of the inside. That's 4x to the third. So it's times 4x to the third times the derivative of this whole thing. So let's say that's negative 1. So times negative 1 x to the fourth plus 27 to the negative 2 power. So that looks really, really hairy, but let's see if we can simplify this a little bit. So this is a hairy problem, clearly. So this is equal to, and now since we have taken our derivatives, we can not write it as negative exponents. I think that'll make things a little easier. So that equals 12x squared over x to the fourth plus 27 plus, or maybe I should say minus, right? Because this is minus times 4 times 4. So minus, let's see, 4 times 4 is 16, and these are multiplying x third, x to the third, x to the sixth, minus 16x to the sixth over all of that. Man, this is messy. Over x to the fourth plus 27 squared. And now let's see what we can do. Well, hopefully this it would have been very cruel to send me a problem that doesn't have a clean answer, but let's keep chugging forward. I think this might end up clean. And what does this equal? Well, let's find a common denominator. Well, this is x to the fourth plus 27. This is that squared, so the common denominator is just that squared. It's a common denominator. Let me write the common denominator. X to the fourth plus 27. And just so you know, it's only teachers or that will actually give you this on homework. You seldom see something this hairy in an exam, but you never know. And you definitely won't see it on the AP exam. They're usually testing concepts, not your ability to chug through a hairy problem. But let's see. Let's do it anyways. Never hurts. So that's our common denominator. So this one is going to have to be that, the 12x squared, times x to the fourth plus 27. So 12x squared times x to the fourth plus 27. And I hope that makes sense to you, right? Because think about it. If we just canceled this with the squared, you would end up with just this term right there. So all I did is I multiplied the numerator and the denominator by x to the fourth plus 27. And then, of course, the second term doesn't change because its denominator was already this. So minus 16x to the sixth. Now let me just erase some of this stuff that I wrote up here, just because I can't erase this because we're going to use this later. So, but I think we're all almost there. So let me use the eraser tool, which is really just drawing a black box. And I think you remember all of this stuff, hopefully. Remember, just so you know, I mean, oftentimes when you're checking through the math, you lose sight of what we're even working on. But we're just trying to figure out the second derivative, and I'm just simplifying this big, hairy equation. And that's actually what this seems to be an exercise in simplification. But so I'll draw a line here, and let me just remind you that I'm working on the second derivative of f. And that equals, just to simplify, so 12x squared times x to the fourth, so that equals 12x to the sixth plus whatever 12 times 27 is. So I'll just write that down. Let's see, that's 2, well, I don't feel like calculating it right now. So 12 times 27, 12 times 27, x squared, minus 16x to the sixth. Minus 16x to the sixth, all of that over x to the fourth over x to the fourth plus 27. And let me see, does that simplify at all? This is 12 times 27. Well, anyway, what can we do now? Well, we can 12x to the sixth minus 16x to the sixth. So what are we left with? Minus 4x to the sixth. Let me figure out what 12 times 27 is. Let's see, 12 times 27. 27 times 12. Let's see, it'll be 54. I don't want to get all messy right here. Let me just get the calculator out. That's always simplest. Let me get my calculator. I should be able to do that in my head, but it's hard when you do it live. 12 times 27 is equal to 324. So plus 324. Man, this would take your, this is wasting paper if you had to do it on a notebook. X squared, all of that over x to the fourth plus 27. Oh, sorry, this was squared, right? If we would take it from down there. Okay. Now, what was the whole point of taking the second derivative? Well, let's answer the different parts of the questions, because I think we finally got this to be second derivative. So let me erase all of this here so we have some room to work. Because now that we've done kind of our mechanical part of the work, we can actually think about what we've just done. This was just our getting to where we are now. That just is how we got to where we are now. And actually, I can even erase this. This is the second derivative. So I can erase all of that work. And hopefully you understand how we got there. And I can even write it. This is f prime prime of x. So let's do the first parts. Find the intervals of increase and decrease. So essentially, where is the first derivative positive and when is it negative? So this is the first derivative, right? So when is this expression positive or negative? When is this expression? So we could have also written this as 4x to the third over x to the fourth plus 27. When is this positive and when is this negative? Well, first of all, the denominator is always going to be positive, right? You take anything to the fourth power, it's automatically going to be positive. At least it's not going to be negative, right? If you put 0 there, you just get 0. But any other number there is going to be positive, as long as it's not imaginary. So the denominator is always going to be positive. So if you want to know when is this positive or negative, the question only boils down to when is 4x to the third positive or negative, right? And so if you want to say when is it positive, well, 4 actually it's kind of, 4x to the third is positive when x to the third is positive. And when is x to the third positive? Well, when x is greater than 0, right? If you put in any number greater than 0 here, this term will be positive. And likewise, when is this term negative? Well, you put a negative number, you take it to the negative an odd number exponent, you're going to get a negative number. So let's say the intervals of increase. So f of x increases when x is greater than 0. And how did we know that? We just looked at the first derivative and we said, when is this greater than 0? The denominator doesn't matter because it's always positive. So when is this greater than 0? When x to the third is greater than 0. When is x to the third greater than 0? Well, sure, when x is greater than 0, right? Only a positive number to the third power is positive. And similarly, and I'll write it in a different color, f of x decreases when x is less than 0, because that's when x to the third is less than 0, which will make 4x to the third less than 0, which will make this whole thing less than 0. And they didn't ask us for a minimum or maximum point, but we do have a critical point exactly when x equals 0, right? Because when x equals 0, we have the first derivative is equal to 0, and we have 0 slope. And do we know whether that's a minimum or a maximum point? Well, let's see. F of x increases when x is greater than 0, so the slope is upwards after 0. And f of x decreases when x is less than 0, so the slope is negative. So right at x equals 0, we must have a minimum point. They didn't even ask us that. But anyway, so let's figure out the intervals of concativity and the inflection points now. So we know x equals 0 is a minimum point. We know When x is greater than 0, we're increasing. When x is less than 0, we're decreasing. And now let's figure out the concativity and inflection. And that's where we're going to use this second derivative. And let me erase all of this just so we have some space to work with. Let's see. Okay. This was a hairy problem. But in the end, all you have to do is chug through the algebra and have faith that in the end something vaguely usable will come out. So find the intervals of concativity. So what we want to figure out is when is the second derivative positive, when is it negative, and when is it 0. 0 is the inflection point. Positive, it means concave upwards. Negative means it's concave downwards. And watch the previous 3 or 4 videos I've done on intuition of concativity, and because I don't want you just to memorize. I want you to always, when you're 50 years old or 40 years old and your kids are learning this, I don't want you to have to go back to the book. I want it to be ingrained in you. Oh, concave upwards just means that the slope is increasing, so that means that the second derivative must be positive, right? You don't have to memorize these things. But anyway, so let's figure this out. When is this positive, negative, or 0? Well, we could use the same logic. This denominator is always going to be positive, right? Because no matter what number you put in here, you're going to get either positive or 0, and you're going to left with 27, you square it. You're going to get a positive number in the denominator. So f prime prime of x, the second derivative, is 0 when this thing is equal to 0, when the numerator is equal to 0. It's positive when the numerator is positive, and it's negative when the numerator is negative, right? Because this is just, this is always going to be positive down here. So let's figure out those intervals. So let's just figure out, first of all, when this equals 0. So minus 4x to the 6th plus 324x squared. Let's figure out when that equals 0. Well, the first thing I would do, if we just let's just divide both sides by x squared, just to get some, get this x squared out of the way. So I get minus 4x to the 4th plus 324 is equal to 0. Let's take that 4x to the 4th onto that side of the equation. But then I'll swap sides of the equation again. So I get 4x to the 4th is equal to 324. Right? I just moved it on that side and then switched. And then I get x to the 4th is equal to, what's 324 divided by 4 is equal to 81. That's a good number. And what to the 4th power is equal to 81? Well, 3, right? Because 3 squared is 9, 9 squared is 81. So x, and this is interesting though, x is what? X is equal to plus or minus 3, right? Because minus 3 to the 4th power is also going to be 81. So x is equal to plus or minus 3. So these are the inflection points. X is equal to plus 3 and x is equal to minus 3. And that's actually just the x values. If you wanted the actual inflection points, you would take f of both of those points. So let's see. So the points, if you actually wanted the actual coordinate points for the inflection points, you would say, let's see, you would say the inflection points, and I'll do them in green for inflection points. Positive 3, and then you'd put 3 back in here, and the natural log of 3 to the 4th, which is 81 plus 27. 81 plus 27 is equal to what? 108. So it's the natural log of 108, whatever number that might be. Right? That's one of the inflection points. If you were to graph that point, you could evaluate this on your calculator and get the exact y value. And the other point is going to be minus 3. And it's going to be the same value, right? Because minus 3 to the 4th is still 81, so it's also the natural log of 108. So if you were to graph this on your graphing calculator, and I encourage you to do so if you get the intuition, these would be 2 of the inflection points, and you would see it because we'd be switching between our concativities then. Fair enough. So between these points, we must be one type of concativity, and then after these points, we must switch. So let's figure out what type of concativity we are between these points. So well, actually, no. I just realized this up here. I shouldn't have just divided both sides by x squared. I should have just factored out an x squared. I should have said, when does this thing equal 0? It's actually, sorry, my mistake. I should have written, I should have factored out, I should have said minus 4x squared. I would redo the video, but I've gone so far into it that I'll just carry forward, and you'll see that sometimes even I do simple algebraic errors. So if I were to factor this out, I get minus 4x squared times x to the fourth minus 81 is equal to 0. So we solved when this equals 0, right? This equals 0 when x is plus or minus 3. And then when else could this expression equal 0? Well, if this factor equals 0. So if x is equal to 0. So the other inflection point, we could say, is also 0, right? Because if you put x equal to 0, the second derivative is also going to be equal to 0. Sorry, I shouldn't have just divided both sides by x squared. In fact, in order to do that, you have to assume that x is not equal to 0. So anyway, I should have just factored it out. And then you'd say, well, either this is 0 or this is 0. My error. So the other inflection point is the point 0, comma what? Well, if you put 0 into the original equation, you get the natural log of 27. So these are the three inflection points. And so, let's see, I think I'm pushing 21 minutes. So those are the inflection points for this. And this was an extremely, extremely hairy problem. So what are the concativities? So all you have to do to figure out the concativities is try x values in between these points. In between these, evaluate the second derivative at x values in between those points. And if the second derivative is positive, you know, it's concave upwards from, you know, let me draw them on a number line. This might be the longest video I ever made. Longest video I ever made. So let's see. We get an inflection point at 0, positive 3, and negative 3. And we already showed what these points are. We could graph them, but that's too much time. But what happens at, let's pick some points. Are we concave upward or downward here? Actually, once we figure out once, we know that we keep switching at every inflection point. So that's all we need to know. So let's try x is equal to 1. So at x equals to 1, what's f prime prime of 1? F, the second derivative of 1 is equal to what? It's equal to minus 4 plus 324. So it equals 320. 320. We don't even care what the number is. All we care is that that number is positive, right? So if the number is positive at 1, that means from 0 to 3, from x equals 0 to 3, we are concave upwards. And so every inflection point we're switching. So from greater than 3, we are concave downwards. And then we're also concave downwards over this interval. And then since we switch at minus 3, we're concave upwards here. Well, anyway, this was a very benign looking problem, but it ended up being much hairier than I thought, and I even made a simple mistake here, but hopefully that didn't throw you off too much. The simple idea is intervals of increasing and decreasing. When does the slope increase? When does the slope decrease? That's saying when does the first derivative increase? When does the first derivative decrease? Concativity, well, the first thing you'd find is inflection points. That's what I would do. That's where the second derivative is equal to 0, and this was extremely hairy, but we found those points. And then the actual points on the graph are these, 3 with the natural log, etc. And then at these points, you're switching between concativity upwards and downwards. So all you have to do is find the concativity at one of the points in the interval, and then at each of those points, they will switch. And I encourage you, we don't have the time in this, I'm pushing 24, 25 minutes, but I encourage you to graph that and verify and see for yourself that the graphs really are concave upwards for all x less than 3 and concave downwards between negative 3 and 0, and see what an inflection point looks like, what these points look like. Anyway, I'll leave it there, and I will see you in the next video.